okay, I want to generalize it to talk about something called a general linear block code. Okay, so the Hamming code is a linear block code. Okay, and the way we generated the Hamming code, way we computed the parity bits, we computed the parity bits by taking combinations of the information bits. We're going to generalize that to multiplication by a generator matrix. So the generator matrix is used to generate the code. It implements the encoding function. So we have the same exact encoding function as before, k bits in, n bits out, okay? And we're going to do some matrix multiplication now. So I'm going to call my input message M, okay? And by the way, this underbar here means it's a vector. And my input message M is a vector of what size? So that's my input is here. So what size is my input? How many bits? Just look at this diagram here. How many bits are being put in? K bits, right? So M is a vector of length K. Okay, and I'm gonna, in matrix notation, its size is 1 by K. Okay, when we write 1xk or 1 times K, that's the size of a matrix. It means it has 1 row and K columns. So it's a row vector of length K. The reason I'm doing this is this is going to help you later, okay? It's going to help you to imagine the sizes being what I'm telling you here, okay? Now a code word, which is the output here, because there's n bits coming out, a code word is of size n. It's a vector of length n. So I'm going to imagine as a row vector of length n, so its size is 1 by n. Now the generator matrix is going to be the map between input and output. It's going to be a matrix of size k by n. And the relationship between m, x, and g is just x is equal to m times g. Okay, so if you remember your linear algebra, you know that when you do matrix multiplication, the sizes have to work out, right? So remember, this is a 1 by k, this is a k by n. So that's good, right? Because we know that, so let me write that here. So this equation in sizes is a 1 by n equals 1 by k, right? Multiplied by k by n, right? You see how that works out? Right, because when you do matrix multiplication, if you remember, when you multiply two things together, the inner things have to match, right? So this is sort of, if you can imagine what's going on here, right? You're going to take an input message, multiply it by g to get x, okay? Okay, so that defines something called the generator matrix, G. Okay, it'll be a K by N matrix. Now we're going to look at examples of G later to show you that what's happening is that G is just computing the parity check bits. That's all it's doing. Again, how many code words are there? Well, there are K bits in, so there are 2 to the K messages, so there are 2 to the K code words. Now, this is for those of you who've studied linear algebra. From a linear algebra point of view, the code is just a span of G. Or another way to say it, it's the code is just all linear combinations of the rows of G. So let's look at some examples, okay? So if G is given by this matrix here, right? So G is, the first row of G is 0, 1, 1, second row of G is 1, 0, 1, right? If I compute M times G, so here we can immediately see that K is 2 because there's 2 rows. Remember, G is of size K by N. So there's 2 rows here, so there's 2 input bits, and there's 3 columns here, so there's 3 output bits. So the block length is 3. So if I look at 0, 0, right, and you multiply M times G, so again, this was the multiplication here, right? 1 by K matrix M times a k by n gives you a 1 by n. So this is good. If you multiply 0, 0 by g, you get 0, 0, 0. If you do that for all 4 of this, you get this. And this is my code, which I've shown here. Okay, so this is the code C2. So this code C2, which is these 3 vectors, this actually is the code from my example on, I think, slide 1, page 1 or page 2, right? Where we added 1 parity bit, right? And if you look at this matrix, when you multiply m times g, what is the parity bit? Can anybody see? There's 2 information bits. This 3rd parity bit, how is it computed as a function of the information bits? So you can see that from what's happening here. When 0, 0 is multiplied by this, what is that 3rd bit? Just look at it. There's a 1 here and a 1 here, right? This 3rd bit is just this times this, right? What this column is telling you is that this last parity bit is just the sum of the first 2 information bits. This one is 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 0. If you go back to C2, we said, oh, let's just take the sum of the 2 information bits. And you see how that's encoded now here in the generator matrix. So this is one possible generator matrix for this code. So we have this code. Now, if I give you a generator matrix, it's easy to compute the code. But given a code, you can also figure out the generator matrix. Okay? Now, this generator matrix, now when I have a code, there's actually no mapping from information bits to code word, right? The code itself is just a set of code words. The generator matrix actually gives you that mapping. But there's no reason why 0, 0 needs to map to this code word and 0, 1 to this. With this generator matrix, the mapping is as given in this table here. But it turns out that I can have many mappings. There's not just one mapping. There are many mappings. So for example, the generator matrix given here is also a generator matrix for this code. For this generator matrix here, what's the mapping between bits and code words? Yeah, it's the same because G is the same. This one is the same as that one. I meant to say this one here. So what is the mapping for this one here? We're gonna swap these two. The set of code words is still the same. That's why I said this is still a generator matrix for this code. Okay, but this is a slightly different linear map, right? It maps 0, 1. So this generator matrix maps 0, 1 to 0, 1, 1, and it maps 1, 0 to 1, 0, 1. The nice thing about this view is that it completely generalizes everything, right? And it will turn out that what's most important to you is not the mapping, meaning the performance of the code will be determined by the code words themselves, but the mapping you need when you do decoding. Yeah, so now we go back to, so let's talk about C3. Okay, so now that we understand this, let's talk about C3. C3 was in my sequence of examples at the beginning, this was our 3rd attempt. The first attempt was uncoded. Second attempt was this one, adding 1 parity bit. And the 3rd attempt was adding 3 parity bits. So let's see if we understand, let's summarize everything that we've talked about. So first of all, what is n for this code? What's the block length? Yeah, the block length is 5. What's the dimension? You have to look at this. There are 4 code words. So if there are 4 code words, then how many bits generated those 4 code words? How many possible values of bits? So your input size must be of size 2. If you have 2 bits, there are 4 binary vectors of length 2, each corresponding to mapping to a code word. So k here is going to be 2. Right? So you can get k from the number of code words. Okay? What's dmin? Like initially, we don't know whether this is a linear code or not. So what you really have to do is compute all pairs. So maybe it's worth checking, is this a linear code? And if it's a linear code, what's the generator matrix for this code? So what will be the size of the generator matrix? So G is going to be a 2 by 5 matrix. So we're going to have two rows. so one way to look at it is when I multiply, I need to get back my original bits here, right? So there has to be an identity matrix here. Then this one looks like it's the sum of the first two information bits. So this would be 1 and 1. And then I'm repeating the first two bits, right? So again, it would just be an identity matrix here. I was able to reconstruct it from how I saw the parity bits being generated. So this is one possible mapping. The takeaway from this is that we can use a generator matrix to compute the parity check bits that we want to transmit. Okay, if it turns out that there's an identity matrix here, then my code words, my messages also end up here. So in this example here, right, we see that the first two bits include my message, but it need not be that case. Please keep in mind that, like, if I use, for example, for this code here, it's instructive for you for this code here, see what happens, what's the mapping from this generated matrix here. Okay, you will see that it's not going to map like, oh, the information bits end up as the first two bits. I did this just to show you an example of what the generated matrix was. Okay. I realized we didn't finish this. Okay. So since I'm able to generate this code via matrix multiplication, what it tells me is that this code is linear. Okay. And G is given here. Okay. N was 5. Whoops. How did that happen? N was 5. K was 2. What's D min? D min is 3, exactly, because of this guy here. Good. So I think we're all on the same page now. Okay. So this tells us, basically, this solves the encoding problem. The way we're going to encode is through multiplication by a generator matrix. Okay. So if you remember, we talked about encoding. Okay. So we're going to encode through a generator matrix. Okay. Now, let's talk about decoding. Now, when we decoded the Hamming code, we decoded by computing the syndromes, right? We did syndrome decoding. So let's see how we're going to do syndrome decoding. Okay. The way we're going to do syndrome decoding is through something called a parity check matrix. So given, so every linear block code has a generator matrix associated with it, and it has a parity check matrix associated with it. Now, I'm always going to call the generator matrix G and the parity check matrix H. Okay, that's to avoid confusion. But I want you to get, I want you to understand the idea. Not just every time you see G, think generator. No, right? I'm going to do that so it's not confusing. But let's talk about what these are and how it's going to allow us to do syndrome-based decoding. Okay, so it's going to help us to talk about it slightly from a linear algebra viewpoint. So G, so the code is all linear combinations of the rows of G. In fact, you saw that, right? Because I'm taking all possible, there are 2 rows here, taking all possible 2-bit combinations. And what am I doing? Every time I look at 0, 1, or whatever, I'm taking all possible linear combinations of the rows of G. Either I take this itself, right? Or, either I take the row itself, which is 1, 0, 1, 1, 0, and 1, 0, 1, 1, 0 is a code word, right? So that corresponds to 1, 0. 0, 1 corresponds to 0, 1, 1, 0, 1. 1, 1 corresponds to the sum of these two, and 0 corresponds to 0 times each of the rows, right? So we see that the code is nothing but all possible linear combination of the rows of G. So that's all I'm saying here. The span means all possible linear combinations. Now, H, this parity check matrix H, is going to be the span of the null space of G. What we mean by the null space of G is like the part now. So remember, these, like all these things sit in n-dimensional space, right? But your code is k-dimensional. So your code is of dimension k, but it sits in an n-dimensional space. So there's these other dimensions here. Those other dimensions are h. So when you look at the span of those other dimensions called the null space, you get h. Okay? So the way I want you to see it is the h is going to be such that GH transpose equals 0. So it's going to be the matrix H that makes, when you multiply it by G, or when you multiply its transpose by G, you get 0. Okay? And what this means is that if X is a code word, then XH transpose is going to equal 0. And the size of this is n minus k, which is the number of redundant bits. So if I have so this parity check matrix, so G was size k by n, and remember all of this stuff sits in n-dimensional space. So since G is size k by n, the remaining dimensions are n minus k. And again, you embed it into n-dimensional space. So H is of size n minus k by n. Now, X was sitting in n-dimensional space. If you multiply X by H, now I need to make the sizes work out. So I have to do X times H transpose, right? X times H transpose is a vector of size 1 by n minus k. Where have we seen that before? Does anyone remember? Like think back to syndrome decoding. This is just the syndrome. So it will turn out that if I take X and I multiply by H transpose, if X is a code word, I will get 0. If X is not a code word, then I will get some value that I can take as a syndrome and I can use to do syndrome decoding. Okay, let's try to understand. Okay, so I'm gonna come down here. So I'm transmitting X, right? It's a vector of length n. Let's say I receive something noisy. Okay, I'm going to receive this noisy vector r, which is X plus some error vector. Okay, now let's compute RH transpose. So again, matrix multiplication is linear and it follows the same rules of addition and distributive things as normal addition. So RH transpose is just X plus E H transpose, which is XH transpose plus EH transpose. And we know that XH transpose is 0. So when you multiply the received vector times H transpose, what you get is EH transpose. So you actually get a look at the error. You don't know what E is, but you get a look at the error. You get EH transpose. And this is called the syndrome. Okay? And what we're going to do is we're going to do the same thing as before. We're going to go through all possible syndromes, and we're going to decide what to do, meaning all possible error patterns, multiply them by H transpose, and figure out what to do. Because I generated the error pattern, I know how to correct it. I'm going to build a syndrome lookup table just like I did for the 7-4 Hamming code. Okay? So the only thing we have to do is, given a generated matrix G, I have to find H. And the way to do it is impose this constraint. G H transpose equals 0. So it turns out either G or H is the code. And in linear algebra terms, the code is a span of the rows of G, or it's the null space of H. I think you don't need to worry about this. This is for those of you who know linear algebra. Okay? I'm going to skip this dual code for a minute. Or maybe it's okay. Let's talk about the dual code. Then I go through some examples. Okay? So if I have a matrix G, if I have a generated matrix G, okay, G gives me a code C. Associated with every G is an H. That H is the H that makes GH transpose equal to 0, right? Right here. Okay, so H is such that GH transpose is 0. So associated with every G, there's an H. Now, if I think of H itself as a generator, I get something called the dual code. For the dual code, H is the generator. For the original code, G is the generator. And for the original code, H is the parity check matrix of the original code. But when I think of H by itself as a generator, I get a dual code. And this dual code sits in that null space that we spoke about, in the other n minus k dimensions, okay? So let's go over an example. So this was the same code that we talked about before, where we are just adding a parity check. So one way to think of this code is you add a parity check bit. Okay. Another way to think of this code is through this generator matrix. Now notice that this generator matrix does not have an identity here. So this generator matrix is not saying 0, 0 maps to 0, 0. Sorry. It's not saying that. Actually, since it's a linear code, all linear codes map 0 to 0. So it is mapping 0, 0 to 0, 0, 0, but it's not necessarily mapping 1, 1 to this, and 0, 1 to this, and 1, 0 to this. It's a different mapping, and you can figure out what that mapping is, okay? So this is, when I consider this generator matrix for this code, let's see what the parity check matrix is. So the way I'm going to do it is I'm going to write out my constraints. So here's G. Now, initially, assume that this is blank. So I have A, B, C, okay? So I want to multiply G. Now, in this case, H is going to be of size 1 by 3. So H transpose is of size 3 by 1, which is why I drew it like this. And I want to multiply this times this, and this times this, and get 0, 0. Well, if I want to multiply this times this to get 0, what does that tell you? What does A and B have to be? I want to multiply this times this. So this is 1 times A plus 1 times B plus 0 times C. So this is just A plus B. If I want A plus B to be 0 and A and B to be non-zero, what do A and B have to be? They have to be 0, 0 or 1, 1. We don't allow 0, 0 because that's sort of catastrophic. So this has to be a 1, and this has to be a 1. And what does the second one tell you? This times this has to be 0. So this tells you that B plus C has to be 0, which means that C also has to be a 1, right? Which is how I got the result that H is all ones. So no, the elements of H cannot be 0. That tells you nothing. If H transpose is all 0, then all your syndromes are 0, right? So that's of no use. So in this instance, for this G, the H is this here. So H transpose is this, and H is 1, 1, 1. Okay, and we can use this. For example, you can now check that for all the code words. Check that code word times H transpose equals 0. What does this say? This says that when you multiply by H, you add up all 3 bits. So do that. Add up all 3 bits, you get 0. Add up all 3 bits, you get 0. Add up all 3 bits, you get 0. Add up all 3 bits, you get 0, right? So for every code word, when you multiply by H transpose, you get 0. So that tells you that H allows you to check if something is a code word. If you receive something and that receive vector R times H transpose is not 0, you know you don't have a code word. But based on sort of this idea here, you're getting a look at the error. You don't know the error, but you get a look at it. You get EH transpose. And we're going to just essentially consider this as the syndrome. Okay. One last thing, this code, this dual code. So if I take this H and I use it as a generator matrix for a code, what code will this H generate? This thing is of size 1 by 3. What's the dimension and block length of the code of the dual code? Each generator is of size what? And so the dimension is 1. That means I just have 1 bit. So 0 times H is my first code word, as 1 times H is my second code word. So my dual code is 0, 0, 0 and 1, 1, 1. Okay? And so these two codes, C2 and C2 perp, are dual. And we can see that they're dual, that they sit in dual spaces, because if I take any code word from here and multiply by the transpose of any code word from here, they will multiply to 0. They're orthogonal. Every vector here is orthogonal to every vector here. So the dual code is just a set of all vectors that are orthogonal to my original code words. I only bring this up because sometimes, and it's not going to affect us, but the dual code is a very important idea because sometimes you can get results in the dual code that is hard to get in the original code. But because there's this relationship, a result in the dual code can often be translated to the original code. So here I'm illustrating two ideas through this example. One is I find a generator for this code. I found a parity check matrix for this code, which is H. Okay, and then you can check that a code word times H transpose equals 0. So that's the first idea. And the second idea is that if I look at the H itself as a generator, I get the dual code. The dual code is related to the primal code. So you can think of it as the original or primal code. The dual code is related to the original code in the sense that it sits in the sort of orthogonal space. Now, but the structure of the dual code is very much related to the structure of the original code. So if you can learn something about the dual code, sometimes you can translate those interesting things to interesting things about the original code. Structures are very similar. They're tied together. So understanding the dual code is almost as good as understanding your original code. I just want to expose to you that there's this thing called a dual code. You have a code generated by a generator matrix, right? That code, okay, has a parity check matrix. So H is the parity check matrix of C. But when you think of H itself as a generator, you get the dual code. And that ties these two together. So the parity check matrix let you compute the syndrome. So just like we did for the 7-4 Hamming code, what you can do, take all possible error patterns, right? And compute the syndrome and build a lookup. Because you're generating the error pattern, you know how to correct it. So now you say, okay, I'm going to find all possible syndromes and what is the correction procedure if I see that syndrome. Now, sometimes you might be right, sometimes you might be wrong, but the idea is that most of the time you'll be right. Okay, there's still going to be times when a different error pattern generates the same syndrome and you won't be able to detect that point. Okay, all right, I think what I'm going to do is I'm going to end here.